Exponential linear unit. This is another activation function which is coming from ReLU family. In the last few lectures, we learned about many activation functions which are coming from ReLU family. What did we learn? Initially, we learned about the standard ReLU activation function. After that, we saw many variations of ReLU. First one was leaky ReLU activation. Then we learned about parametric ReLU activation and also about randomized ReLU activation. When we were learning about this, we first understood why each of these were required, and thereafter we saw what exactly are those activation functions. So in this lecture, we are going to learn about ELU or exponential linear unit. So first thing we want to understand is what exactly is the requirement of exponential linear unit and what is this particular activation function. What did we learn previously? ReLU was brought in order to avoid vanishing gradient problem. It was successfully able to avoid or solve the vanishing gradient problem, but it introduced dying ReLU problem. This was an even larger problem, and in order to get rid of that, not even larger, but still this was causing issues in our training. Because of this, we had to come up with leaky ReLU. So leaky ReLU solved dying ReLU problem. But what did it do? It introduced a new problem called as the problem with fixed hyperparameter alpha. This is what leaky ReLU did. After that, we went in search of what can be done in order to avoid this problem with hyperparameter alpha. That is when parametric ReLU came to rescue. It solved this problem, but then it introduced a new problem called as overfitting. Because of the training that was done on alpha, it was doing overfitting on alpha. Because of this, we had to come up with randomized ReLU, and it was able to solve this overfitting problem as well. So this is where we stopped the last lecture, which was on randomized ReLU activation function. So the question is, what are the problems that we are still looking at? What is it that you want to solve using ELU or exponential linear unit? So we'll first outline two problems that we want to mainly tackle, and then we'll see how we are tackling those problems using ELU. Okay. So the first problem we want to look at is, this is already a very common one. We had seen in all the previous ReLU lectures that you want to make sure that dying ReLU problem is taken care of. At the same time, there should be as lesser consequences as possible. So this is what is the first thing you want to achieve with ELU or exponential linear unit. You want to make sure that dying ReLU problem won't be there, and you want to minimize the consequences that you have to face while you're solving the dying ReLU problem. This is the first thing. Second thing you want to do is, you want to push your activations towards or closer to mean of 0. So there is this question of, why do you want the activation to have a mean of 0? Okay, understanding this is very important. Why should you have 0 mean activations? 0 centered or 0 mean, this what it generally does is it makes your optimization easier. Why are you even having this activation function? The whole point is, when you have a larger neural network, if you have these activation functions, they will introduce nonlinearity, and then it will make your optimization easier. So whenever your activation function is having 0 centered outputs, your optimization will become easier and easier. This is why you will always go for 0 centered outputs. I know you will have this question of how exactly is this optimization getting easier. Okay, so we are getting to that. In case of ReLU, let us take standard ReLU activation. What happens in case of standard ReLU? Whenever you are having a positive input, let us say some positive input, then your output is also positive. This is what happens with standard ReLU. But what if you are having a negative input? In all those cases, your output is 0. It is not negative, it is 0. What does this mean? After the ReLU activation, or if you take all the outputs of ReLU activation, you either have positive values or you have 0. This means the mean is always greater than 0. So this is the problem that is called as positive mean activation problem. Okay, positive mean activation problem. What is this problem? The activation function output is always on the positive side, which means there is a bias towards positive side on the output. Because of this, so what is going to happen when you have this bias? This is what we want to understand. Let us say you have a large neural network. There are a lot of layers here. Then the neurons in the deeper layers, let us say if you take any of the deeper layers, they will always receive inputs that are positive shifted. That is because even if you are having negative inputs to come at the beginning, the initial layers of ReLU, they will convert all those into either 0 or positive, which means by the time you reach these deeper layers, everything that you receive will be on the positive side. So this will create a bias, and what happens? Your gradients will become unbalanced. So this is the bigger problem. Whenever your gradients become unbalanced, what will happen? Your learning will be slower. Your learning will be slower. And what happens to your weights? Your weights, what is the purpose of weights in the neurons? You want to train it such that in each neuron, the weight will be perfectly set in order to give you the best possible output. This is what you're going to train. So whenever you are in this situation where your learning getting slower and all your gradients are unbalanced and it is all positive biased, what happens? Your weights will have to always adjust in order to compensate for this positive bias that you're causing. Okay, so this is the problem that you're facing with general ReLU or standard ReLU activation. Because of this, your positive gradient dominating, your optimization will always go zigzag. When your optimization is zigzag, it is difficult to converge onto one particular minima. What are you doing during optimization? Whenever you are doing optimization, you want to come down, 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 and finally reach a particular point called minima. This is what you are attempting. But if this optimization goes zigzag, then it will be difficult for you to converge onto one particular minima, right? So when you face this problem, your convergence will become slower. In order to tackle this, what do you want? You want to make sure that your average or the mean is close to 0. Why is it not close to 0 here? It is because you don't have anything on the negative side. In normal ReLU, you have everything on the positive side and only 0 on the negative side. Because of that, you have positive bias. Your mean is shifted on the positive side. But instead, if you are able to come up with some function which is having equal representation on the negative side in some way, then you will be able to avoid this problem of positive bias and you will be able to take the mean closer to 0. See, I'm not saying you want exact 0 mean, but in case of ReLU, it's always positive. So you want to bring it somewhere closer to 0. This is what you want to do. Okay, so this time we'll first see the mathematical formulations and after that we'll go to the graphical side, because at least in understanding this, I think that will be easier for you. So first we'll see the mathematical side, what is the difference. Then we'll see graphically how exactly ELU is working. Okay. On the mathematical side, if you see the ELU function, ELU of x, this will give you a value. Remember, this is from ReLU family, so the behavior will be similar. Okay, so it will give the value x in all cases of x being greater than 0. So this is where it is similar to ReLU family. I'll just draw the graph here. In case of normal ReLU, I'm drawing the graph of normal ReLU here. It will be on the positive side, y equal to x line. On the negative side, it will be 0, right? It will be with 0. This will be the line of normal ReLU. But if it is something like, let us say, leaky ReLU or something, on the positive side, you will have the same thing. But on the negative side, you have a slight tilt towards negative. That is why it is leaky. Okay. Coming back to our problem, ELU. We'll draw the graph of ELU later. For now, I just showed you what happens with normal ReLU. Okay. This is red is ReLU. And what happens in case of leaky ReLU. Okay. Leaky ReLU is blue. This is what I have shown you. We'll see what happens with ELU. Okay. In case of ELU, whenever x is lesser than or equal to 0, how you are going to handle it is, you will say the value is alpha into e power x minus 1. So this is where the exponential part comes in. See, when we were discussing about ReLU, the rectified linear unit, we had discussed about why exactly is it named as rectified linear unit. What did we explain? We explained that on the positive side, ReLU is behaving similar to y equal to f of x. This would y equal to x or f of x equal to x. So y equal to x, this is a linear line. So that is where it is behaving linear on the positive side. That is one part. Next part is what exactly is rectification here. So coming to, we had actually discussed about what exactly is the rectification logic. So we had seen on the negative side, it is doing rectification similar to the concept in signal processing. So in signal processing, rectification means changing the negatives to 0. That is either cancelling out the negatives or changing the negatives to some positive value. This is called as rectification in case of signal processing. We are taking the concept from there and we are going to rectify all the outputs on the negative side by making it 0. That is why ReLU was called as rectified linear unit. The same way, why is ELU called as exponential linear unit? Can you make a guess this time? The linear unit part, that is same, because on the positive side, behavior is going to be same. It is that you have a y equal to x line, which is linear. That is why it is called linear unit. But why is it called exponential? Because on the negative side, you are having a exponential function. Because of this exponential function, you are calling it as exponential linear unit. Okay. So this is the logic behind ELU. What happens now? So, okay, one thing, here is a hyperparameter alpha. So let me first point out this here. There is a hyperparameter alpha here. This alpha, this is a value which you have to, which actually controls how ELU value will change. What you generally do is, you can keep this as 1. So this is a general usage that alpha will be kept as 1. But this is a hyperparameter. You can change it to whatever value you want according to your particular scenario. But a general convention is you can set it as 1. Okay. Next thing is x, you already know x is your input value and you have alpha, which is your hyperparameter. After this, what happens for positive inputs? Whenever you are having a positive input, you are going to use f of x equal to x, which means it is a very linear scenario and it is the same scenario for the whole ReLU family. Okay. What happens with the negative inputs? Whenever you are having a negative input, this time you are going to have an exponential curve. So this part is the difference between your other ReLU functions and ELU or exponential linear unit. What is going to happen here? This exponential curve, I'll draw it now. We'll take a different color and this is how your ELU is going to look like. Okay. In your ELU, you on this side, it's a straight line, but on this side, you have an exponential curve which saturates after some time. Okay. It's an exponential curve, but saturates after some time. What did you understand here? So I'll mark it as ELU. Okay. It is this light blue line. If you see this line, ELU line, what you can understand is it approaches the value minus alpha as x becomes more and more negative. So let us understand how this is becoming. If you see the value of x from here, from this formula, alpha into e power x minus 1. This is what happens during negative scenario. Now think, you are going very negative. That is, you are going towards the end of the negative, very large negative value. If that is your input, then what happens? Your value of x, this will be a very large negative number, right? If your value of x is very large negative number, then your e power x will be like 1 by e power x, where x is a very large positive number. Okay, so e power x, here you are having a negative value of x, which is like you are having 1 by e power x, where you take the positive part of x. That means this term is going to go closer and closer to 0 as you increase the value of x on the negative side. Okay, not on the positive side. If you are increasing on positive side, the formula is simply x. But on the negative side, when you increase the value of x, the power e power x, this particular value will go closer and closer to 0. Why is it? It is 1 by e power x, where x is a positive number. So when this x becomes larger and larger, this 1 by e power x will go closer and closer to 0. So when it approaches 0, what happens? This will be 0 minus 1, which is minus 1. So finally, you can consider it as minus alpha. This is how, when x becomes more and more negative, this curve will approach minus alpha. Okay, it will approach minus alpha. What are the other points you want to understand from this graph? There are two more things that you want to understand here. First thing is, one very big advantage is that if you see any other ReLU curve, you will see a sharp turn at x equal to 0. So here at the point x is equal to 0, you will see that suddenly the function will totally change its shape. That is what happened in case of all the previous ReLU functions. But this time, for exponential linear unit, ELU, you can see it is much smoother. So this time you have something which is differentiable. Okay, so you have a smooth saturating curve. So for negative inputs, it's not like previous ReLUs where it is a very small slope. You have comparatively larger slope here, which means you have greater chances of producing zero-centered outputs. Okay, which is not more positive-centered like the previous cases. This will be zero-centered. Let us see the derivative now. It's important to understand derivatives whenever you are understanding activation functions. So ELU of x, you know it is this. What will be the derivative? ELU dash of x, the derivative will be, what about the derivative of x? The derivative of x with respect to x is 1 only. So this will be 1 if x is greater than 0. The question is, what happens when x is lesser than or equal to 0? This is the interesting case. So the answer is, the derivative of this can be written as ELU of x plus alpha. So now you may be thinking, how did I directly write this ELU of x plus alpha? Let us solve that first. So we'll understand how that came. And so then that will make the picture clear. Whenever you are doing any mathematical works, any sort of even differentiation or anything, you should actually know how exactly it came. Do not ever by heart this. But automatically, after some time, if you see this again and again, you may automatically have this in mind, but understand how it is getting derived. Okay. So let us do this derivation, d by dx of, what are you going to take derivative of? This particular one, alpha into e power x minus 1. Okay. So if you take derivative of that, of alpha into e power x minus 1, this can be written as d by dx of alpha into e power x minus d by dx of alpha. You can write it like this. Here, what is the derivative of alpha with respect to x? There is no x term here, which means derivative of alpha with respect to x will be 0. So this will go off. What remains? Derivative of alpha into e power x. So this time you can write it as alpha into d by dx, derivative of e power x. What is the derivative of e power x? It is e power x itself, which means instead of this, you can write e power x. So the derivative is alpha into e power x. What I want to do now is, I want to bring it in terms of this ELU. So I want to bring it in terms of this particular value. What I'm going to do is, I'll do minus alpha plus alpha. So this thing is 0. If you do alpha minus alpha, it will be 0. So I'm simply adding minus alpha plus alpha. What is the point of adding this? What I'm going to do is, I will say this is alpha into e power x minus 1 plus alpha. And what is this term? This term is same as the term here, alpha into e power x minus 1, which is ELU of x. So this is what I'm going to do here. I'll say this is ELU of x plus alpha. So this is how we got this particular term here. Okay. So you understood how we did the derivation for this. What did you understand from this? What happens to the derivative? The derivative is 1 for all positive values. So whenever you have positive value here, you know derivative is always 1. But the important part is what happens when the value is negative. So derivative actually tells you about the slope. For negative values, you understood it is smooth and differentiable, plus it starts at alpha. So when x is equal to 0, what happens? At this point, it starts at alpha and it approaches 0. If you see this, it is approaching 0, this particular value, when x is going to very large values, that is infinity. On the negative side, if x goes to very large values, it is approaching 0. How is it approaching 0? Because if you see this particular value, alpha into e power x minus 1 plus alpha. If you take this value, when x is going very large on the negative side, what happens? E power x value, it will go very close to 0. So this will be 0 minus 1. So that is minus 1. Alpha into minus 1 will be minus alpha. Minus alpha plus alpha will be 0. So the slope will become 0 when x becomes very large. That is what we are seeing here. When x becomes very large on the negative side, okay? On the negative side, when x becomes very large, slope approaches 0. So initially slope is large and then slowly slope is approaching 0 with time. This is how on the negative side it is behaving. What about the positive side? On the positive side, slope is always 1. This is it about ELU. Now think, what advantage are you going to get because of this ELU function, the exponential linear unit? What advantage are you going to get? First thing is, you know it is smooth and differentiable here. So this gives you stable and efficient optimization. What is the whole purpose of this activation function? You want to make your optimization easier. You want to make your convergence faster by introducing, that is even after introducing non-linearity into neural network, you want to see how you can make your optimization faster or convergence faster. So when it is smooth, the curve is smooth, it is easier for you to have a stable and efficient optimization. Before we conclude this lecture, we'll just have a look at what are the problems caused by this ELU. Okay, so whenever you learn something, you should know what exactly are the positive sides and also what are the problems caused by this particular function. So coming to ELU, problems caused means we are doing a comparative analysis. We are going to compare with other ReLU family functions. Okay, we are not going to compare with everything. Compared to other ReLU family functions, ELU is comparatively, okay, so comparatively it is having a higher computational cost. The computational cost is higher because of the exponential calculation. That is, you want to calculate e power x compared to other ReLU functions where you simply want to output x when it is positive and maybe output 0 when it is negative, or maybe you want to output alpha x when it is negative. If you compare with that, e power x is a difficult computation. So your computation cost is going to be higher on the ELU. Another thing is, it also requires hyperparameter tuning. Because you have this hyperparameter alpha, you will have to do tuning of this hyperparameter. I told you can keep it as 1, but otherwise you want to tune this hyperparameter alpha. And one more thing you can think is, uh, generally in your normal neural networks, let us say you are having some layers, it is better that you go with the normal ReLU or maybe leaky ReLU, something like that, which is simpler. But the effect of this ELU, this will be visible only when you have deeper networks. If you have deeper or complex networks, that is when the effect of ELU will become visible. Otherwise, if you're having a smaller network, you're training it, it is easier that you go with normal ReLU or maybe leaky ReLU. Those things are better options. Okay. When you have very large networks or complex networks, in such cases, you can go with ELU or the exponential linear unit. So in this lecture, we learned about why you need exponential linear unit, what problem it is solving. Then we learned about the mathematical formula, how it is coming from, why it is called as exponential linear unit. Then we saw graphical representation. We understood how it is different from normal ReLU or other ReLU family functions like leaky ReLU or parametric ReLU. And then we found the derivative, how it is coming up. We saw the advantages, disadvantages, where it can be used. Okay. So this is what you want to learn about exponential linear unit.